Welcome back, everyone. So today we are going to learn about chapter 16, which talks about aromaticity and what it means for a molecule to be aromatic. Okay, so there are generally 4 rules of aromaticity to follow. 4 rules of aromaticity. Okay, so rule number 1 is all atoms in the ring, all atoms in the ring must be sp2 hybridized. Now notice I didn't say all carbons, which means we could have oxygen, nitrogen, sulfur, as well in the ring instead of just carbon to carbon bonded rings. Now sp2, they all have to be sp2. Alright, so rule number 2, and we'll talk about what it means to be sp2 or how to find sp hybridization in once we do examples. Now, rule number 2 is that they all have to be closed, planar rings. Okay? Now, closed means that if all the atoms are connected, there should not be a gap. And then planar essentially means so planar means less than 8 carbons. Once you go beyond 8 carbons or 8 carbons and above, you start to fold on itself. Okay, a 8-membered ring, a octene with 4 double bonds, it will start to form a structure called the tub. You might recognize this term in your lectures or your PowerPoints. So always keep that in mind. Ideally, we want 6, 7, or 5. 4 and 3 are also okay. Third rule is must be fully conjugated. Now, we talked about conjugated systems in the past 2 lectures, which we're dealing with double bonds and resonating in a system. Now, fully conjugated obviously means throughout the entire system, on every single atom, there must be some type of a conjugation system that is involved. Okay. Now, fourth rule, perhaps the most important rule, is the Huckel's rule. Okay. So Huckel's rule is, now there's 2 different types. So there is 4n plus 2 equals number of total pi electrons found within the ring. Okay. Now, an example of electron numbers that would fit this pattern are 2, 6, 10, 14. Okay, and then so all of these correspond to a stable form called aromatic. And then again, all of these are pi electrons, and we'll talk about how to count pi electrons and how to apply this equation that we have. Now, before I move on, we also have another equation for Hawkins rule. Okay, so instead of 4n plus 2, we have 4n. So this is the number of total pi electrons, but now the numbers are 0, 4, 8, 12, 16, and so on. Okay? Now, this list is not exhaustive. It can obviously go on forever, but these are the typical numbers you'll deal with. Now, if it's any of these numbers and it follows every other rule, it's going to be anti-aromatic. Okay? So Huckel's rule and all of the rest of the rules apply to both aromatic and anti-aromatic. Now, the only difference between aromatic and anti-aromatic is Huckel's rule, which aromatic has the equation of 4n plus 2, and anti-aromatic has the equation of 4n. Now, n equals an arbitrary number. Okay, so n could be any number that needs to be fit into our total pi electrons that will give us the right equation, the right number, and we want a whole number. Now, once we start counting pi electrons, it'll start to make sense how to apply these equations. Okay, now, so we talked about aromatic, anti-aromatic, but last thing there is non-aromatic. So if one or more of the above rules are broken, then the structure is non-aromatic. So some ways to identify if it's non-aromatic or not, or aromatic or anti-aromatic. Non-aromatic are always open rings, not fully conjugated, sp3 atoms, or has odd number of electrons, okay, of pi electrons. Let me clarify that. All right, so pi electrons just means that electrons that are found in the pi bond, which typically means that those electrons can resonate across the entire ring. Okay, that's why it has to be fully conjugated for us to count pi electrons. Alright, so now that we know the general idea of what a structure is, aromatic, anti-aromatic, and non-aromatic, I'm going to draw up a table to showcase a little bit more to put this in terms. Alright. So there's the entire rules. If you want to take a screenshot of or write it in your notes, I would highly recommend knowing this and memorizing it for now. Eventually it should just come as second nature. Alright, so if we were to rank by stability, the order would be aromatic. Let me zoom in a little bit. Non-aromatic. And lastly, anti-aromatic. Alright? So just to refresh, in terms of stability, this is so we'll talk about stability and Huckel's rule. So for aromatic, it's stable, and it has 4n plus 2, and it could be, again, 2, 6, 10, 14, 18. Non-aromatic is unstable. Sorry. Non-aromatic is, regular. It's not too stable or too unstable. It's all right. All right. Now, non-aromatic can have any number of pi electrons. Now, they don't necessarily have to be an odd number, but if it is odd number, odd equals automatically non-aromatic. Okay? And then lastly, anti-aromatic is unstable. It has the Huckel's rule equation of 4n, and it has the pi electrons of 0, 4, 8, 12, 16, 20. Okay, any of those. Alright, so there you have it. Another table of some sort to distinguish aromatic, anti-aromatic, and anti-aromatic. And then here's the full view of everything we've done so far. Alright, so now I'm going to talk about some molecules that apply to each of these. So first, I'm going to start with a benzene ring. So we'll have a section for examples. So when you think of aromatic compounds, the first thought should come to your mind is a benzene ring. Now, a benzene ring and an aromatic compound have been used interchangeably in the past, whether it's in Chem 1 or Chem 2. But now we'll actually talk about why that is the case. Now, let's go through the 4 rules. So all atoms in the ring must be sp2 hybridized. Now, all atoms mean we are looking at this carbon, that carbon, that carbon, this, and that. So if you notice, all of those are sp2 because a carbon with a double bond is most likely 90% of the time are going to be sp2. Now, obviously, you can quickly check your hybridization just to double check if it's sp2, sp, or sp3. So we got that rule checked off. Now, does it look closed? Yeah, all the atoms are connected. There are no gaps, so that fits our rule. Is it planar, which means does it have less than 8 carbons? So benzene ring has 6 carbons, which again is planar, fits our rule. Is it fully conjugated? Okay, remember, fully conjugated or a conjugated system means we have a double bond, single bond, and a double bond, okay? And this has to go all around the entire ring for it to be considered fully conjugated. So if you notice, So we have a double bond, single bond, so double, single, double, single, double, single. Okay, so that means we are fully conjugated in our benzene ring. So that rule also applies. Now, lastly, if the first three rules apply, that means it is not non-aromatic. That means either it has to be either aromatic or anti-aromatic. So all that there is left to do is count how many pi electrons there are. Okay, so remember how to count pi electrons is a double bond equals 2 pi electrons, negative charge that is resonating with the pi system are 2 pi electrons, positive charge 0 pi electrons, and then I guess also a triple bond is 4 pi electrons. Now you could also have a radical. A radical would be 1 pi electron. Now remember, these can only be a pi electron if any of these electrons, compounds that contain electrons, are resonating in the conjugated system. Okay, if they're not, if they're on the outside of the ring, and they're not even close to the conjugated system, then we don't count in the total pi electrons of our ring. Okay, so once that is understood, we can go ahead and count how many pi electrons we have. So here we have 1, 2, 3 double bonds, which means 3 times 2 gives us a total of 6 pi electrons. Okay, so 6 pi, let's see if it fits. Yep, we have 6 pi electrons right here. That means it is anti-aromatic. Sorry, it is aromatic. Let me correct that. So instead of just memorizing the numbers, if it's aromatic or anti-aromatic, you can use the equation 4n plus 2 to identify if it's aromatic or anti-aromatic. So 6 pi is equal to 4n plus 2. Subtract 2, you're left with 4 pi electrons equals 4n divided by 4 divided by 4, pi electrons equals n. Okay, now we want pi electrons to equal n. Now n could be any arbitrary number, so keep in mind, as long as it evenly splits on both sides, then you're good. You did your job. Alright, so that's why a benzene ring is aromatic. So let me label this. Benzene ring. Okay? So let's take a look at a few more examples of what it means to be aromatic or anti-aromatic. So give me one moment to draw all these out. Feel free to skip ahead till I drew all of these to save some time. Alright, so there you have it. We have all of our structures. However, I am going to add a positive charge on the first column, a radical in the second column, and then a negative charge in the last column. Oh, I forgot my double bonds on this. Alright, so now I would recommend you pause the video, go ahead and take a shot to identify all 9 compounds, if it's aromatic or anti-aromatic or non-aromatic, and then see if you got it right. Okay, so I will count my pi electrons in orange, but the reason why I'm starting with this step is eventually you should be able to quickly do rules 1, 2, 3 in your head. So if you look at all of them, they are closed planar rings because they are all connected. There's no gaps, and they are all under 8 carbons. And to see if they're all sp2 and fully conjugated, any atom, in this case, in all of these cases that are carbons that have a charge, will automatically become sp2. So even though, let's take a look at the first example. So even though this carbon has 1, 2 hydrogens, you might think, oh wait, it's sp3, but really that positive charge is going to take care of one of the radicals. Okay, sorry, one of the hydrogens. So it is 1 bond here, 1 bond there, and then a bond to hydrogen, making it sp2. Same case for this. Alright, and then same for the other one. So yeah, as long as it has a charge, it's considered sp2, and it's also considered fully conjugated, because that charge is participating in the ring. Okay, so all that there is left to do is identify if it's if it's anti-aromatic or aromatic by counting our pi electrons. Okay, so in this case, the first one, going left to right, left to right, left to right, we have our cyclopropane. We have I see 1 double bond and a positive charge. Positive charge again, remember it's 0. So I have a total of 2 pi electrons. Here I see a double bond and then a radical. A radical is 1 extra pi electrons, so it's going to have a total of 3 pi electrons. Now, as soon as I said 3, there should be a trigger going on in your head saying 3 is an odd number. It must be non-aromatic. We'll get to that later. So double bond, negative charge, 4 pi electrons. 2 double bonds, 1 positive charge, 4 pi electrons. 2 double bonds, 1 radical, 5 pi electrons, and then 2 and 1 lone pair, giving us 6 pi electrons. 3 double bonds, 1 positive charge, so again 6 pi. 3 double bonds, 1 radical, 7 pi. 3 double bonds, 1 negative charge, 8 pi electrons. Okay, now let's assign if it's aromatic or anti-aromatic or non-aromatic in purple. So 2 is going to be aromatic, 3 is going to be non. In fact, we can assign all of the middle column as non because they are all odd pi electrons. Okay, now 4 pi, that will fit our 4n Huckel's rule. So 4N, if you remember, if I scroll up, it's going to be anti-aromatic. So this one is anti. Again, I see another 4 pi, anti. And then I see a 8 pi, which is anti-aromatic. And then lastly, I'm left with two 6 pi electrons, so it's going to be aromatic. Okay, so alright, so there you have it. So let me know if you have any questions on that. Feel free to email me anytime, or yeah. Alright, so some examples of a quick way to see if it's non-aromatic. I talked about it right here. Essentially, if it looks like this, it's going to be non-aromatic. And if it looks like this, with just one double bond, but these carbons are all sp3 and they're not fully conjugated, again, non-aromatic. So non-aromatics are the ones that are actually easier to spot out. And then if we have a 8-membered carbon or cyclooctene with 4 double bonds, giving us 8 pi electrons. Now 8 pi electrons, you might get that confused with anti-aromatic, but because it has 8 carbons, it's going to start to fold on itself because the pi orbitals start to overlap, and when they do, they bend slightly towards each other, giving you a boat structure. Sorry, a tub structure. So let me see if I can draw it. Okay, 1, 2, 3, 4, 5, 6, 7, 8. So there's a double bond there, 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 and there. Okay, so that's what it looks like in a 3D model. So this is the 2D version of it, and this is the 3D version of it. Alright? Okay, so we have 2 more things before we are done. So again, if you need to take a screenshot, here are the 9 examples along with the benzene ring. And then if you need to take a screenshot of everything, not able to fit it, but that's as close as I can get. Alright, so we have a few more cases to talk about, such as the oxygen. Let me use a thicker brush. Okay. So the oxygen with 2 double bonds and 2 lone pairs. Okay. Now, you're going to be like, okay, I see 2 lone pairs. Lone pairs are probably all participating in the resonance structure, so it must be 2 double bonds plus 2 lone pairs. I have a total of 8 pi electrons, which you would be wrong. So let's see why that's the case. Okay, so I'm going to count our pi electrons in orange. So we have a double bond, and then when we have 2 sets of lone pairs, we only count 1. Okay. The reason why is when we take hybridization into account, first of all, you might even realize, oh wait, oxygen looks like it's sp3. I have 2 sets of lone pairs and I have 2 bonds. It must be sp3 because I have 4 electron domains. But remember, anytime you assign hybridization to an atom, you have to take resonance into account, which means that you have to see if there are electrons on that atom that can move around or be delocalized and exist in the p orbital instead of the sp3 orbital. Okay, so and that's exactly the case here. So if you notice, oxygen is technically sp2, which is why it also fits our pattern. So if you put O in the middle, put trigonoplanar, we have one bond there, and then one set of lone pair is existing in the sp2 orbital, and then another set of lone pairs are sitting in an unhybridized p orbital. That's why this set is, so it's p orbital, so that means pi electrons, but this is the sp2 orbital, making it sp2 pi electrons. Sorry, not pi, sp2 electrons. Okay? We only count pi electrons, which only exist in the p orbital. Okay? So again, the reason why this oxygen is sp2 is because this set of lone pairs can resonate around and it's delocalized. So it exists on the oxygen only sometimes, and then even though it's sp3, it's technically sp2 along with a unhybridized p orbital that exists every now and then. So together you get sp3. Alright? So this is the case for oxygen as well as sulfur, because remember they're both in the same category, in the same group, so they both have two sets of lone pairs. You only count the ones that I circled. Okay, so again, don't and do count. Erase that. So don't do count. Okay? Hopefully that made sense. I'm also going to go over nitrogen, because nitrogen also has a special case. So let me label this section for special cases. So special cases. And then we talked about oxygen. Now we will talk about, if I can zoom out. Okay, I guess that's the most zoomed out it's going to get. Nitrogen is going to look like this. Okay, so there are two ways I can draw nitrogen in the ring. I can draw it like this. Or I can draw nitrogen that contains a double bond. Now, only 1, 2, 3, those count, and only 1, 2, 3, those count. So both of these are 6 pi electrons, but for different reasons. Okay. So again, here you count. Here you don't count. Don't count. Okay. Does anyone know why? Okay. So the reason why is on structure 1 compared to structure 2. Structure 1, nitrogen has one set of lone pair, and that lone pair can resonate with these double bonds on its left and right, so it's going to be considered delocalized, which means it can move around in two and exist in two different places, which is why it's in the p orbital that we talked about above. Now, the lone pair in the second molecule, it does not have a choice of existing in two different places. Okay, nitrogen is stuck in a sp2 fashion. It has a double bond here, a lone pair here, and a single bond there. Okay. So this lone pair is in the sp2 orbital, which is why we don't count it in our total pi electrons. Okay, but here are, again, if we were to draw it, single bond, hydrogen bond, and then lone pair in the p orbital. Okay, so we do count it. So this is the pi bond. Okay, that's why it exists in the pi electrons. Alright, so hopefully that made sense. It could get a little bit tricky and it will trip you up in the beginning, but hopefully by the end of it you are an expert. Okay, so lastly, before I end this off, I'm going to give you a full-blown exam practice question where you have to apply all of these rules. Okay, so the question will read, rank by solvolysis. So if you guys remember what that means, solvolysis is a SN1 concept where the nucleophile is also your solvent, okay, and this only applies to SN1, okay, so this means SN1. Now they won't put this in parentheses, but this is what you have to understand. So SN1 also means we prefer tertiary, secondary, primary, carbocations. Alright. So 1 equals most stable. Okay? Alright, so now let me put the structures up. Alright, so I have written down all 5 compounds, and I have a kind of a checklist to go through each molecule to help you rank this question. So first things first, how many pi electrons are on each molecule? So let me use my color, the right color. Okay. So before we do anything, I forgot. So when it says rank by solvolysis, SN1, what is SN1 or even SN2? What does that mean? So that means a leaving group leaves and you form what type of charge? A carbocation. So you have to replace all of these chlorines with a carbocation. Okay, so we are going to place that in the color green. So just pretend the chlorine's not there. And just pretend that, well, you don't have to pretend, there is a carbocation there, so you can now rank it, okay? Remember, carbocations don't have any pi electrons, so don't include it in your total pi electrons. So first molecule, I see 2 lone pairs, but I only count 1 set of pi electrons because this set can still resonate with this charge. So I have 2 pi electrons. Okay, so second molecule, I have 2 double bonds, 1 set of lone pair. Again, I'm just going to go ahead and circle all of these just so we don't get them mixed up in the future. So I have 6 pi here, 6 pi here, 4 pi here, and This is also 4 pi. Okay? Now, based on this and based on everything else, all of our 4 rules, let's assign aromaticity to this. Now, right off the bat, the quickest thing to observe is I can see some sp3 carbons. So this should be easy. It's going to be non-aromatic. Okay? Now, second molecule, everything's fully conjugated, everything's sp2, it's 6 pi electrons, so it's going to be aromatic. Third molecule, same exact concept, that extra bond on that charge does not make a difference as of right now. It's still gonna be aromatic. So let's talk about this boron. Okay, boron typically has 3 pi electrons. Now boron is also an exception. So let me write that a little bit to the side. That I forgot to include earlier, and you might have to know this for a quiz or an exam. So boron is accepted as being involved in the conjugation system. Okay, so if you notice, boron is sp2 because it has 3 electron domains, and boron, we can bypass the conjugation rule because it is technically involved. If you want to learn more about why that's the case, I would refer to your professor or the textbook because they would know more. But as of right now, we can accept that boron is accepted in the conjugation system. Okay, so this has 4 pi electrons. It's going to be anti-aromatic. Okay, and then lastly, I see 2 more carbons that are sp3, non-aromatic. Simple. Okay, so just based off this, if we were to rank these using red, just based off this, aromatic has to be either 1 or 2, and then anti is obviously number 5, and then my non is either 3 or 4, okay? So at the very least, you can get kind of some estimates, okay? Now, position, what do I mean by position? Okay, position only applies to this carbocation. Now, this carbocation is secondary, tertiary, secondary, okay? Not too hard, a Chem 1 concept, easy to find out. Now, the only difference is this middle structure, which is tertiary. Now, we can only compare that with, so let's actually put all these in this row. Secondary, tertiary, secondary. Now, the reason why we have this checklist is because in row of aromaticity, in the second row of aromaticity, we have a tie between 2 aromatics and a tie between 2 non-aromatics. Now, looking at the third row, position of our carbocation, and looking only at our aromatics, one is secondary, one is tertiary. Carbocations prefer tertiary, so this is going to be number 1. And the only other aromatic compound left, this is going to be ranked 2. Now, between our non-aromatics, let's make this 5, so we just have 2 to worry about. Between our non-aromatics, they're both secondary, so what do we look at next? It's going to be resonance, okay? Now, remember, resonance is almost always good It also applies in this case because you are making it more stable across the entire molecule. So you want to assign how many resonance structures each of these molecules have. Now, this one only has one because it can resonate with that lone pair right here. That charge, you're looking at resonance with that charge. So that charge can resonate with this lone pair. Now, we don't need to do the middle columns, but we can go ahead and do it. This has 3 res, 2 resonance, and then this one also has 2 resonance. Okay? It can either, the resonance is either here or here. Okay? So we're comparing 2 versus 1. 2 is obviously better than 1, so that's why this is 3 and this is 4. Okay? So here's the completed problem if you want to take a screenshot and refer to it. Okay? So let me scroll up slowly. Let me start from the beginning just in case you guys want to see it more in detail, or pause the video or take a screenshot. Alright, well there you have it. We talked everything about there is to know about aromaticity. I suggest doing some more practice problems and applying the rules of aromaticity to any compound you see, because there will be a section where you have to do that, so it's better to be prepared for that than be caught off guard. So next week we will probably cover chapter 17 and talk about orthometapara and what it means for something to be an activator, deactivator, electron withdrawing group, electron donating group, and the week after that we will actually get into the reactions of aromatic compounds. Okay? Alright, well until next time, see you guys.